Hello, everybody. Welcome to SRA 365. I'm, of course, Professor S. This is this week's lecture, and it is on chi-square tests. Okay, so before we go into what the heck that is and how we find it and all that stuff, thing is, it's like there is a lot of material that we are covering today. Technically, with the chi-square, there is so much that we're covering it in 2 modules, right? There's a visual representation that comes right after this. But in order to kind of make sense of what's going on with that, we got to understand a lot of the basics of chi-square, and that's what we're covering today. So we're going to talk about what it is, how to find it, and honestly, there's like a few different things that we're covering, right? Because there's a one-way, there's a two-way, and there's 2 ways that we will be finding the 2-way, and then things that I'll help you for the lab that's for this week. Okay, so this stuff on the side, I'll be referring to that as we go along, so it's nice and easy to follow along throughout the whole video because it's gonna be a long one. So without further ado, let's start by talking about what the heck chi-square is. So chi-square, maybe you notice that I say chi and it's a x squared, right? So the idea is it's not an x, it's the Greek letter chi. The idea is like what we're doing is we're looking at the relationships of 2 categorical variables, and we're seeing, well, not just 2 categorical, there could be just 1 categorical variable, and seeing the relationships within that variable. But the idea is it's looking for relationships with categorical variables. That's what it's doing. So one way, we're looking at one variable and its relations kind of within itself, right? The proportions, the probability that you would expect each one of those things, that sort of thing. We'll get into what that is in just a second. But the idea is one way is with one variable, 2-way is with 2 variables. There's not a 3-way or a 4-way. We actually cover that kind of later. But for the moment, we're just talking about 1-way and 2-way. That's the only way that you can do a chi-square test. Okay. And so the idea is like well, we'll get into like the 1-way in just a second, but the idea that we find all of the chi-square values is we have observations and we have the expected values. And so we take the observed, the observation of that something occurs minus what we expect it, square it, and divide by the expected value. And we do that for all of our observations that, which we would pair with its respective expected value. You know what? Let's just begin and let's just keep on going. So anyways, let's start with the 1-way. And I have 2 examples to kind of help explain this further. So with the 1-way, remember that's 1 variable. And I'm going to use this example, the text examples, because the text doesn't really go into 1-way. And by it, I don't think it goes into it, but we will go into quite some detail to kind of make sense of it because I think it helps make sense of the 2-way by understanding 1-way. But anyways, we notice that this is like a table that you can make from the data that's given in the text, and I'll refer to the text script and data in just a second. But the idea is like if you look at the amount of attacks for Canada, Mexico, and US, Canada is 61, Mexico is 134, US is 105. Okay. And so the idea is like our null hypothesis is that there is no difference in the amount of terrorist attacks in the 3 different countries, right? The alternative hypothesis is that there is a difference in the amount of terrorist attacks in the 3 countries. In other words, it is more likely that a terrorist attack will happen in one country over another, right? And this is what we observed, right? So if you look at what we observed, Canada is less, Mexico is more, and US is less than Mexico, but not by much. And so notice that, like, think about like what would we expect if there was like no difference in the amount of terrorist attacks? They'd all be the same value, right? But I mean, like the idea is like, just like if you flip a coin so many times, right? It should be 50-50, right? But are you always going to get the same amount of heads and same amount of tails? If you don't believe me, try it. Flip a coin, let's say 10 times. Are you going to get 5 heads, 5 tails? Maybe, but it's also like there's a randomness that occurs that like maybe you get slightly different. Does that mean the coin is weighted? No. The idea is like it's just that's just the way randomness works. It could be just a little off. And so the idea is like if it's a lot off, that's when we kind of wonder if it's significance, and chi-square helps us figure that out. Okay, so anyways, I'll help illustrate that a little further when we're thinking about this. So notice Canada is 61, Mexico is 134, US is 105. And so when we think about what we would expect if we did this, like I think there's 300 observations. So if we look at 300 observations, we would expect 100 to be Canada, 100 to be Mexico, 100 to be US, right? Because it's just as likely for each way to occur. And so the idea is, just like any other hypothesis testing that we're doing, we're trying to show that we're testing, like, our data is different, but is it enough to suggest that the null is wrong? In other words, is there enough to show that it's not that they're not all the same, right? That's what a whole hypothesis is. Is it enough to say that it's not that null hypothesis, right? So when we combine the observed and the expected, right? This is like, remember when I was talking about the observed and the expected? Yeah, this is what we're using to come up with the chi-squared amount. And so what we do is we find we use the observed, we subtract the expected, we square that difference and divide by the expected amount for each one of those three. And when you add up each one of those quotients, you get 27.02, right? That's our chi-square value. And then what we do is we put that in the distribution and we see the p-value. If the p-value is low, then we reject the null and say that it's, we reject the null, right? So what does that mean in English? The idea is like the p-value, remember that's the probability that what we, that given the null circumstances, that what we would occur is normal. So the higher that is, the more expected it is. If it's really low, then that seems really unlikely that the null is true, is essentially kind of what we're saying here, right? So anyways, we put this in the distribution in the p-value that we get, and I'll show you how to find the p-value in a little bit, but the p-value ends up being this, where it's about 0.000000136. I think I had enough zeros in there. Sorry, I wasn't counting the zeros when I was talking. But the idea is, it's like, that's definitely lower than 0.05, which is our arbitrary cutoff point, right? So which is enough to say that they're not evenly expected, right? One would be more expected than the other, or one would be less than the others, right? The important thing is that they're not all the same, okay? It doesn't say how much more or anything like that. It just says they're not all the same. So maybe we want to rephrase it, and we say that the there's a proportion to the text, that it's 1 to 2 to 2, right? So we use those odds. And so the alternative is that it's not that, that the proportion is not 1 to 2 to 2, right? So in order to do that, we have to think about what would be the expected values if it was 1 to 2 to 2. And so when we do that, we get this table up above. We get Canada, which is 60, Mexico, which is 120, and US, which is 120, right? So that seems a lot closer. Here, let me put the values back in there, or the expected values. So we have the expected values with 60, 120, or sorry, that's the expected value. The observed values, sorry, are 61, 135, and 105, which is much closer to like what we got here. But they're not the same, but is it enough? That's what we're going to be looking at here. But how did I get the 60, 120, 120? So the idea is like, when we think about 1 to 2 to 2, if you add all those up, 1 plus 2 plus 2, that's 5, right? So if you think about each one of those is the numerator over 5, that's the probability that we would expect that thing, right? So 1 over 5 would be Canada, 2 over 5 would be Mexico, and 2 over 5 would be US. That's where I got those. And so 1/5 of 300 is 60, and 2/5 of 300 is 120. Okay. So anyways, that's how we got it. So anyways, when we do the chi-square, we get 3.525, which means that the p-value is 0.172, which means that we can't reject the null. There's not enough evidence to reject the null. It's not our observation is not very unlikely given what we were expecting. Okay. So that's how we find the one way. Now let's go into RStudio and I'll show you how to find the one way in RStudio. All right, so clearly in RStudio, and this is the script that the text give us. We'll come back to this when we get to the two-way. Okay. Anyways, I'm going to be using the same data here, and so that when we run it, I'm going to call this attack data as the data. And so then if we look at it closer, so I'm going to look at, since we're doing one way, I'm going to do a table of the attack data, specifically country. Okay, so attack and my mic stand is getting in the way, country, and then when I run it, there we go. So Canada, Mexico, US, right? This is the stuff that we got in the last whatever it's called, that we saw in the slides. Okay. So anyways, in order to do the one way, what we have to do is we have to come up with we're going to use the chi-square test. Well, we'll use the expected values, but then we also, or the observed values, but then we also have to provide the probabilities that we would expect. And the way that they're looking for numbers. So the way that we'll do it here, we'll calculate the probabilities real quick. So for example 1, we have the probability. Remember, it was even, right? So it was like 1/3, 1/3, 1/3. That's how we evenly have each one of those things. So we'll do 1 divided by 3, 1 divided by 3, and 1 divided by 3. And so that when we run this, notice that the prob is like 0.333, 0.333, 0.333, right? The idea is it's like it's not really 1/3 is what it sees. It sees the number 0.3333333, so on forever. Well, as far as it keeps track of it. Okay, so it's really more of a quotient of what it keeps track of it, and so it's kind of a close enough. So anyways, what I'm going to do is we're going to do the method for the one way is the chi-square test. And so we put in our observed, which is actually in order to do the observed, we have to store it as something. So we'll actually use this table right here. So we'll do let's do new line here. There we go. So we'll call this observed, and then we'll have this right here. So the observed is that. And so then what we're going to do is we have the observed, P equals the probability, and then we have the, we need correct equals false. And we'll talk about what that means later. But remember, this isn't saying that we don't want it correct. It's that we want this thing to be turned off, and it's not going to actually be an issue really for the one way, but the idea is it's a good habit to get into, and I'll reiterate that later. All right, so anyway, so we run it and notice that it is 27.02. We have a degree of freedom of 2, and the p-value is really small. Okay, so notice that since it's really small, that's enough for us to reject the null, and that we can reject the null, that it's not evenly likely for one of those that attack is going to be in one of those countries, right? So remember when we're doing the hypothesis testing, and I know I'm going to reiterate this a couple times with the hypothesis testing. The hypothesis testing is that we're assuming the null is true, and we're saying, all right, given that the null is true, what is the likelihood of what we see to be true? And so notice a low p-value means that it's really unlikely that what we observed would be true if the null was true, which means if it's that unlikely, then maybe it's not that. That's what we're doing. We're suggesting that it's not that. Okay, so in this case, if we assume that they are just as likely, or if that's our null, is that they're just as likely, with the p-value like that, it doesn't seem like our observations would be very likely to occur. So that's enough for us to say that it's not likely. Now, remember for the second example, we had different probabilities, right? And so it was 1 to 2 to 2. So remember how we calculate that? Like we add those up and we got 5. And then we do 1 divided by 5, 2 divided by 5, 2 divided by 5, right? So let's do the, let's see, we need an observed and we need a prob. And so we'll do the probability first. So remember it is 1 over 5, 2 over 5, and 2 over 5 here. And the observation, it's still the same. Oh, shoot. It's tough typing with the arm here. It's essentially, our observation is still the table, right? Let's get a space in here, make it look nice. All right, so, and then once again, the chi-square test is the observed. And then since it's one way, we need a p equals, and then we'll do the prob, and then the correct equals false. Okay. And so that when we run this, and you want to select the whole thing, run it, and notice that we get a higher, or a chi-square that's 3.525, degrees freedom is 2, and the p-value is about 0.17126, right? So that's a really high p-value, so that means not enough to reject the null. It doesn't mean that the null is true. It's just saying that we don't have enough evidence to say that it's not true. Okay? All right, so now that we showed the one way, let's go back in the slides to talk about the two way so we can show you how to do that too. Okay? All right, so now that we've talked about one way and we've gone through 2 examples, let's talk about what the two way is. And we're going to go through one example, and eventually I'll show you 2 different ways to find it. All right, so the idea is for this is that we're going to be now comparing 2 different variables for this, right? So if you look at the data set, there's type and then there's country, right? So we already went through country. Now we're going to look through type. And so our null hypothesis is that there's no difference between the different types of terrorist attacks and the different countries. In other words, there's no relationship between the countries and the type of attacks, right? The alternative is that there is a difference between the countries and the type of attacks. Or in other words, there is a relationship between the countries and the types of attacks, okay? So that's what we're going to be doing. And so we're going to be using the same formula, but it's comparing 2 variables. And so in order to come up with the expected values, we have to do a little bit more work. Well, a little bit more work has to be done. I'll show you what I mean. So first of all, we have to come up with the totals of the rows and the columns. So first we'll find all of them. I thought I was going to do the different countries and then the types of attack, but no, I'm not. Anyways, and so when I total them up, this is what I get, right? So the total for biological is 115. The total for chemical is 55. The total for firearm is 70. Other is 31. Radiological is 29, so on and so forth. And then the grand total is 300, right? That's how many total. So if you add 115 up, 55, 70, 31, and 29, you get 300, right? Also notice that if you add 61, 134, and 105, you also get 300. The idea is that that's the row column. So all of Canada, that's 61, all of Mexico, that's 134, and all of US, that's 105, which should sound familiar because that's the totals that we came up with for the one way, right? That was our observation. So that was the proportion of terrorist attacks, or at least the observations, right? So anyways, we got to use these totals to help in our, we use these totals to come up with our expected values. And the way that we do that is we'll fill out this table. And so we'll do the expected value for each one of these so that we can pair it with the observation and do that sum that we did before, right? And so the formula that we have for the expected value is the column total times the row total divided by the grand total. And when we find out what each one of those are, it's about this, okay? And so here's the, we'll just move that up here and we'll combine these so that we can find our chi-square. Because remember, we have our observed and our expected, that's what we need. And so when we plug them into that formula, we get about 50.01, which has a p-value of about 0. A bunch of zeros, 407, right? I'm not even going to try this time. But the idea is like, that's really unlikely, right? So that's enough for us to reject the null if our cutoff is the 0.05, which means it's a lot of evidence to suggest that there is a relationship between country and type, right? So it doesn't tell us like the strength of those relationships, or it doesn't tell us like which ones are significant or stuff like that. No, this just tells us about the if there's a relationship or not. The one other thing before I talk about the how we find it in RStudio is the standardized residual. See, that tells us how significant each one of those expected values or the observations is, right? So the idea is the standardized residual takes the observed minus the expected divided by the square root of the expected. And so what that does is it tells us how severe of an expectation that is, or how much that differs. And the idea is like, it's kind of like a z-score. And so we're going to think about the absolute value is greater than 1.96. It's statistically significant. So for example, if you were to go back in time, and which you can rewind. But anyways, if you go back, you'll look at Canada's radiological attacks were observed to be 14, and we came up with the expected value to be 5.897, right? So 14 is a lot more than the 5.897, right? So when we calculate the standardized residual, we get about 3.337, which, if you notice, that is greater than 1.96. So we would say that's significantly more than what we would expected, right? So that's significant. That's how we can kind of gauge like how strong one of these observations is from what we expected. Standardized residual. The next thing that we're going to talk about is the effect size. The effect size, you kind of do it in two ways. The effect size is the like if we just have a 2x2, and actually they kind of all work out to be very similar. But the idea is, idea is like we use the phi to calculate the effect size. If it's a 2x2, and then we use Kramer's phi for everything else. But anyways, the way that we find it is the square root of the quotient of the chi-squared divided by the sample. That's for the two-way, right? That's what the phi is up there. And then we have the Kramer's phi, which has the square root of the chi-square divided by the sample size, but we're going to add a degrees of freedom, or I should say multiply degrees of freedom to the sample size. So that's the difference. So we're going to multiply degrees of freedom in the sample size of, or in the denominator for the Kramer's phi, but we don't for the phi. The way that we find the degrees of freedom is we look at the columns in the row, specifically columns -1 and rows -1, and we use the smallest one. Okay, it's different than the degrees of freedom of chi-square, which I haven't talked about yet, but the important thing is that it's different, and you'll see that when we go through the walkthrough in just a second. But anyways, the cutoffs that we use, or that we're going to use for this class, is that it's very small if it's less than 0.1, right? And it's small if it's between 0.1 to 0.29. It's moderate if it's 0.3 to 0.49. It's large if it's 0.5 or larger. Okay. And so the idea is that, remember the chi-square tells us if there's a relationship. Effect size, in this case, phi or Kramer's phi, says the strength of that relationship. And that's what we're finding here. Okay. Now, there are some things to kind of think about that the text gives, is that there is the Fisher's exact test, which is the easiest way to when doing a 2x2 contingency table, and it's often when the expected value is less than 5. Okay. And we'll get into assumptions in just a second, but like expected values less than 5 is kind of a red flag and means something bad for chi-square. But anyways, the likelihood ratio, this is a test that compares the observed frequencies and those predicted by the model. Or large samples, this ratio will be fairly similar to our typical chi-square value. Anyways, another thing that I need to point out is the Yates correction. Okay, so this is what this does is it takes the chi-square and it modifies it to help it out. It applied, let's see, it says that it applies a correction to our chi-square value by subtracting 0.5 from our residuals before squaring them. The idea is like we don't want it, okay? And it's something that you have to consider when you're doing one of the ways when we're doing the chi-square. It's the correction. Oftentimes people argue that it overcorrects the problem of small amounts and produces chi-square values that are too small. So really for the sake of this class, we're not using it. We won't be calculating Fisher's exact test. Really, we're not going to be doing likelihood ratio either. But the idea is that I want to bring your attention to it because it was in the text. So the idea is it's kind of good to know these techniques exist, even though we will not be testing you on these, or they will be, and they won't be you will not see them in the labs either. Okay. All right. So anyways, before we go on to how you calculate it from the different ways, the one other thing that we need to talk about is assumptions for chi-square. So the first is that there's independence from the observation. So each observation contributes to each observation contributes to one cell, right? So think about it this way. So when we're talking about the attacks, when we're talking about let's say radiological and firearms, and we're talking about Canada, right? So that means that attack can't be both radiological and firearm. They have to be distinct. Otherwise, it voids this thing, right? The grand total has to be all the observations that we're seeing. And so if you have the overlap, then you're going to have more observations than what you observed. Okay, so really, truly, like the idea is, it's like we're assuming that each observation contributes to just one cell. Okay. The other thing is that the expected frequency for any one cell is not less than 5, right? So our expected frequency for anything can't be less than 5. And we talked about this in the last slide. For contingency tables larger than 2x2, it's okay a little bit to have up to 20% of your expected values to be below 5, but none should be below 1. Okay. So really, like the biggest thing to keep in mind is not less than 5. I mean, we're going to be working with a table that's more than a 2x2, so it's different, but like rule of thumb is like 5, and if it's like not a 2x2, it might be okay. So just to kind of keep that in mind. Okay. It's not really where I want to put my emphasis. What I want to put my emphasis is on how to actually find it. And so we have two different ways to do that. We have the text method and we have my method. So what we're going to do now is I'll show you how to do the text method. And then when we come back here, I'll show you my method. Well, we'll talk about like the pros and the cons. We'll talk about my method, its pros and cons. I'll show you that sort of thing. And then we got some more things to cover, right? All right. So anyways, let's go to RStudio right now and I'll show you how to do the text method. All right, so here we're back, and this is what we're going to be using for my way. The way to show the text way is using the script from the text. Here's the text script, and notice that it illustrates everything that you need to do, right? So it talks about like, here's the data. We have that already in there. You need to install Gmodels as the package in order to run this. And so I already did, so I'm not going to run it again. But once you do, then you have to do library to install the package to be able to use it so that you can run the method here. And so it's cross table, and then you put in the two variables that you need. Fisher is true, chi-square true, expected true, srizid true, format equals SPSS. You need all these things here, right? And once you do, you get this amazing data to help make sense of things. The one thing that I kind of want to show you is that notice that when I do run here, like when you look at the data, it kind of looks like a jumbled mess. So if you get like a jumbled mess, play around with the windows, and you can kind of see it here. And so notice that we have biological, chemical, firearm, other, radiological, row total, Canada, Mexico, US. So it kind of looks like the table that we made before, and it has the column totals, the row totals, the grand total, and then notice it has a bunch of different numbers in each of the cells. If you want to know which each one of those are, scroll up a little bit and it tells you what they are. So count. So those are our observed values, right? The first value is the count. That's the observed value. Next one, expected values. So notice we have each one of these expected values is what we have here. And then we have, well, let's see, the standardized residual. That's the last one. That's what we have here. It calculates the standardized residual all right there. When we're ready to look at the chi-square, here it is right here, right? And the degrees of freedom right here. And notice it's a little bit further than what I had said before because I rounded. Has 8 degrees of freedom, and it has the p-value is 4.0 whatever, right? Or 7 zeros, and then 4068979. Okay. Let's see, what other things do we need to do? So it has the total observations. Let's see, error in the Fisher exact test. I mean, don't worry too much about the Fisher exact test because we won't be using that. We just talked about it like that was 2x2, and notice this isn't a 2x2. So that's why it's on the struggle bus so much. Anyways, I think this is pretty self-explanatory. Let's go back to the slides. I'll talk about like the pros and cons of this before I show, and then I'll talk about the pros and cons of my method before I talk about what it is. So let's go back into the slides and take a look at that. Okay. All right. Now that we're back into the slides, let's kind of talk about the pros and cons to using the text method. So the thing is like the pros is like all the information is in one spot, right? But I kind of feel like that's also a con because you get overloaded with information. Usually when you're looking at any of that stuff, you're looking for a little bit of information. And so you have to parse out the things that you don't want, right? Parse out maybe not the best word, but the idea is you get what I'm talking about, right? The idea is that you have to go through and say like, oh, I don't really want that value, or I really want that value, whatever. The idea, another pro though is that the text, since it's from the text and whoever came up with that text, they also did the lab, and so there's like similarities between how it's done in the lab. I mean, you can use my method to fill it out, and personally I would, but I can also see like you want to use what the text says because that's going to be kind of more along it. The cons are that as you saw before, there's a lot of arguments to enter things in, more than the other method. And so I think that's like one of my favorite things about it. The other thing is like you have to use the Gmodels package, which is probably the weakest of the cons on the list, right? Because all you have to do is do library and boom, there it is. So there you go. There's the pros and cons of using the method that's prescribed in the text. So now what we're going to do is we're going to talk about my way. So the idea is like for my way, it's kind of a little simpler, but the idea is like if you want to get a lot of those things, you have to do a couple more steps, but it finds that thing, right? So it finds the chi-square and the p-value. And if you need the observation and the expected values, you can do like a couple steps and get it. It's not that big of a deal. The idea also is that it's native to R, so you don't have to install any packages or run the packages. It's all right there. But like the cons is that you're given lots of tables, which could be a plus. You want to have a table of expected values, a table of observed, table of standardized residuals. It's up to you. Yeah. Another con, and this is very important, I will emphasize this in just a second when I show you how to do it, is that you have to turn off Yates correction, right? That's what you have to do when we do, well, you'll see the correct equals false. That's what we're doing, is turning off Yates correction so that we get the normal chi-square, because for whatever reason, well, it's not always on. It's on certain situations. It's whenever it's a 2x2, it'll turn on. But we always want it off, so we'll always do correct off. Oh, we've already done with the one way. That's kind of my way of doing it. And notice that we had correct equals false. That's to turn off Yates correction. So we didn't need it for the one way per se, but it is a good habit to get it in. All right. So anyways, let's go into RStudio and I'll show you how to do the two-way test my way. Here, clearly I'm back in RStudio, as you can see. All right. And so now what we'll do is my way. So first, and what we're essentially going to do is we're going to use this method right here, chi-square test. But it actually ends up being a lot easier than one way. So the idea is first we need to have our observations. And we need to use the table function. There's also xtabs, which we'll cover later. That also works with chi-square. But anyways, but I'm not going to cover that in this video. So anyways, we do table, and then we have the attack data, and then I want to do this. There we go, country, and then attack data type. And then when we look at it, I want to just look at what this looks like. Boom. And so notice that we get these, it gives our observations in this nice little table. Isn't that great? So, I mean, one way to get our observations right here is just do that table that we calculated right here. Or if you didn't store that as a variable, boom, right there. All right. Anyways, the other thing, or what we could do, yeah, we'll just leave it at that. Let's do, sorry, I'm thinking about all these different things all at once. All right. So anyways, now for actually doing the chi-square test. So it's just chi-square test. We put it in the observation, and then we do the correct equals false. Once again, good habit to get into. There we go. Here's our chi-square. Remember, it's 5.001 degrees of freedom, 8. P-value is really low, right? And that's just to put in perspective, same thing as what we got before with the books way or the text way. We don't have a book in this class. So anyways, that's how you do it, right? So I think I'm just playing with you. We got other things to talk about. So let's talk about like the getting the chi-square observations. And actually there's another way that we can get this. So let me just do the, I'm going to call this attack test, and I'm going to store that to it. And from this chi-square test, there's when we store it as a variable, we can get all sorts of fun things from it. Like the observations. Look, if we do attack test, notice that one of the things is observed. So, right, so that when we run it, it gives us that that tally table that we had before, right? Similarly, if you notice there was other things that we had in there, we can also do the expected attack data. Oh, no, attack dot test. And it was expected. And there we go. There's our expected values. So notice, like, it's nice because you have the observations in one table and you have the expected values in another. Isn't that great? The other thing is that when we're coming up with standardized residuals, like you saw like standard, like there was like something that was like it. notice that there's this looks like it's standardized residuals, but it's not. Here, let me show you like a good way to kind of do it so we are well practiced with it. We can use our um, our our formula that we have, which is observed minus the expected divided by the square root of the expected, right? And so I'll just fill these in like here. We'll just do the expected, right? So that's what the exp is. And the observed, heck, I'll just use this to be consistent, right? And so that's how we find each one of the values. Oh, I want to do parentheses around it because order of operations. Well, actually, you want to see something cool with the parentheses? If we select what we want and then do parentheses, it does parentheses around the whole thing. We don't have to do open and close parentheses. It's neat, right? All right. Anyways, so when we run it, standardized residuals, and then now we can, you know, what's helpful is that, I mean, like this is the same information we got before, but the idea is it's like we want things that we're looking for the absolute value is greater than 1.96, right? So look at this. What we can do is we could do ABS of this. And now we don't have to work so hard to get those absolute values. Maybe it's overplayed, but whatever. All right. Anyways, to do the grand total, what we could do is we could do sum of observations. That's probably the easiest way to do it. 300, right? Now, for doing the effect size, remember this is a degrees of freedom. It's not 8. I didn't talk about how you find that, but the idea is like degrees of freedom for chi-square is found by you taking the rows or the columns minus 1 times the rows minus 1, right? So when we're finding the degrees of freedom for chi-square, the degrees of freedom, remember it was 8. That's because it was, how many are there? 1, 2, 3, 4, 5. So 5 minus 1 is 4, and 3 minus 1 is 2. So 4 times 2, 8, right? So that's the degrees of freedom for chi-square. But when we're doing degrees of freedom, I'm going to just do df for here for the effect size. It's the smaller of the two. So we have a 4 and we have a 2. Which one's smaller? Clearly it's the 2, right? So that's what we're going to do, is the 2. Or we could be even a little bit more helpful and do 3 minus 1. Right? I mean, it's the same number, but it like helps us say like, oh, 3 minus 1, that's how we found it. And so then for the effect size, what we're doing is we're doing the square root of the chi-square, which in this case, I'll just run it here and we'll get the chi-square here. Chi-square divided by, and oops. In this case, the size is 300 times the degrees of freedom. There we go. There we go. And so that gives us our effect size, right? And the reason why we're multiplying the degrees of freedom is because it's not a 2 by 2, right? It's a 5 by 3. So we have to use the Cramer's V. And so that when we do, we get, oh, I didn't run the degrees of freedom. Boom. Here we go. And so we get 0.288704, which is small, right? Let's see, do I have anything else? No, I think that's good enough for here for doing the calculations in R. Let's go back to the slides and we'll finish this up. All right, so we saw my way, and now we got a couple of things we got to clear up. So anyways, if you haven't noticed on the slide so far, is that a question on the lab could ask, what would the value of a chi-square need to be statistically significant? Okay, and remember, statistically significant means that the p-value is less than 0.05. So if we know what 0.05 is, we well, we know about that area, right? Because I mean, like the idea is it's like we have this area under the curve, and this is the p-value. And so the idea is we're kind of working backwards, right? So we had the chi-square before, and it is, well, I mean, it calculates the chi-square and determines the p-value, but this is kind of working backwards. And so in order to do that working backwards, we can do that very easily in RStudio with the q chi-square. It's this the q CHISQ, and then that's the method that we're using. And so then notice that if we're looking for 0.5 with the degrees of freedom of 4, lower tail false, this will give us our what that chi-square has to be at that location right up above me, right? So the idea is like, so the 0.05, that's the area under the curve, that's, or the p-value, right? 4, that is the degrees of freedom for the chi-square. That kind of helps us know what the shape is of the chi-square, to be honest. But and then the idea is the output would be about 9.48779, right? The idea is like it helps us return what the chi-square is at that point. Okay, so we know that it's the chi-square that is greater than that would have a p-value less than 0.05. Okay, so that's how you can answer that question. Okay, now the last thing that I need to talk about is there's a question that asks you for the standardized residual if the observed value is different. And so what you need to do is you look at the observed values on the table and recalculate the expected values with that new observation. Okay. Then you have to recalculate the expected value and the standardized residual by hand using the formulas that we've talked about previously. Okay. So anyways, I think that's enough. Am I right? Anyways, hopefully you found this helpful. I will talk to you all later. Bye. Hey everyone, hope you enjoyed that video. If you did, please press the like button below. It lets me know I'm doing something right. If you have any questions about any of the content, please send a message to both me and the rest of the teaching team in Canvas, and we will get back to you as soon as possible. Don't send it through normal email. You will not get as fast response. If you have any suggestions for how I can make these videos better, please leave in the comments below. Don't forget to roundhouse kick the subscribe button and ring the bell to get notified for the next video. Anyways, I think that's good for now. See y'all later. Bye.